All right, so I sent you this website. It has the syllabus and some other documents that are of interest to you. First of all, the 4 exam dates are right here. I made them real big so you can see them. Those are not likely to change unless there's some, unforeseen thing that goes on. So just go ahead and pencil those into your calendar. This is Physics 151. This is probably like my favorite course. I really enjoy this course. I think because I learned some things that y'all already know, things about the human body, because a lot of y'all have had anatomy, right? Anatomy and physiology. So we'll do some very basic stuff that you've already learned in anatomy, sort of basic functions of the human body. But then we also apply that to the physics of the human body and how physics is applied in those areas. Good morning. And as I said, this is intended for athletic training majors, but allied health majors, not for biology majors. So if you're a biology major, you're in the wrong place. So it will not count for your degree. You will need this book. I have a copy. You'll have reading quizzes from this book that before we actually cover the chapter or as we're covering the chapter. And I'll pretty much follow this book along the way. It's just sort of a paperback. It's not terribly expensive. You can find it in the bookstore. I think used it's about $30. On Amazon right now, the price has gone up before the semester started. It was cheaper, but now on Amazon it's about $20 to $25. So you can also rent it from either Amazon or at one of the various bookstores. But you can read the book, okay? Because we'll follow it pretty closely. First reading quiz will probably be next week. So on chapter 1. You'll also need a clicker. If you don't have a clicker yet, you can get them in the bookstore. You can get either kind of clicker. I know that you guys don't use clickers that much, but a lot of courses on campus do. You can use either one of these. So this is the older type clicker, and this is the newer type. I think this is the only one sold in the bookstore. But you can try. They sell these in the bookstore? I don't think so. You can pick these up online if you want to use for free. So I'm okay with either one. But you need to get those soon. We're going to start using them, if not today, on Tuesday. And I'll tell you what that credit goes towards. These are outcome objectives and our content. Basically, we cover all the topics that we would normally cover in a 2-semester physics course. But there's basically little or no math, and we also throw in some biology things, anatomy and physiology. So it's a fun course, I think, but with a lot of material. But very, very little math, unlike, say, Physics 101 or Physics 201. These are tests. We'll have 4 exams. There's no final, but our last exam will be on the day of the final. Okay. You'll also have reading quizzes. Now, the reading quizzes will be short, multiple choice, 5 to 10 multiple choice, matching, those type questions, maybe 1 or 2 sort of fill-in-the-blank questions. They'll come from the reading. So if you've read the chapter, then you should be fine on the reading quiz. I won't pull out the minutiae. I'll try to pull out the main ideas from the chapter, but they will come from the chapter. And that material also might not be something that we cover in class. But I'll cover all the material in the chapter, but sometimes I might skip over some topics that you could see on the reading quiz. Is that clear what I mean? Reading quiz comes from the reading. And I think it's useful for you to read the book. So that's to help you read the book. There are 5 quizzes. Actually, there are 5 quizzes that I will count, and I guarantee you at least 6 quizzes. So at least 1 drop. Usually I get more than that, 7 or maybe even 8. So hopefully we'll be able to drop more than 1. You'll at least get 1 drop quiz, but hopefully 2 or maybe 3 drop quizzes. Okay? Is that clear? I guarantee you 6, and hopefully we can get more than that. It sort of depends how we go along. You'll also do a presentation. This will be on the very last day of class. You can select a topic in the book that you wish to explore further, and then you'll present your findings to the class. And I'll put out a rubric. I don't really have a grading rubric right now. This is the first time I've done this presentation, but you'll do that on the last day of class, 5 to 7 minutes. It's worth quite a bit. It's worth 150 points. Students tend to do better on these things than they would on an exam. So I do this to sort of help your grade. In case you don't do very well in the exam, then this will pull up your average. So it's meant to help you. It's not meant to just be a tedious exercise. But it's also, if you find something that you're very interested in about the physics of the human body, it allows you a venue to explore that further. Okay? More about that later. Also for class participation, I find that students who come to class, that just devote that 3 hours a week coming to class, that they really do a lot better in the class just because they're devoting that 3 hours to the material that we're on. And so we'll use the clickers to ask questions in class, and the points that you accrue on for those questions will go toward your class participation credit. That credit is worth 50 points. And when you click in on your questions, if you get it correct, you get twice the credit. If you get it incorrect, you get half the credit. Now, I don't really know how many questions we ask. I have some that I've already printed out, and I intend to ask you. But as we go along in the class, I'll ask a lot of questions just in class, just impromptu questions. So by the end of the semester, I intend that almost everybody's going to have that 50 points of credit. But I know just from past that there are some students that aren't going to come to class, and you're not going to max out those. Right? So in order to max out the credit, you need to come to class regularly. Is that clear? If you miss 2 days of class, that's not a big deal. But if you miss 10 days of class, then you're not going to max out that at all. You might get 30 of the 50 or 40, but you're not going to get it. Is that clear? Let's come to class. I think it's good for you. It'll be helpful. It'll help you on the test. It'll help you in the class participation. It'll help you on everything. All right, so that gives us 800 points total. Let's see if I can zoom this in, actually. All right, so that gives us 800 points total. You have 400 points on the exams. 200 points are reading quizzes. Remember we said we had 5 reading quizzes. We dropped the lowest one, and they're each worth 50 points. So that's 200 points. And the presentation is worth 150 points, and the class participation is 50 points. So I just add up all your scores, and I divide by 800 normal grading scale. This is an example of a student. It's not a real student, but an example of how to calculate your grade. All right, any questions about that? That seems clear to you? Okay. Makeup, if you miss, let's see, makeups for quizzes will be case by case. If you have an excused absence, then you can make it up as soon as possible. So please contact me as soon as possible. If you have an unexcused absence, you slept late, you didn't want to come, then you deduct 15 points from your grade. And then 5 points for every day until you contact me. So there's a penalty if you just miss it. And then if you're dishonest in any way, usually I just treat that as a 0 on the assignment, and then I report you to the college. They keep records of all that business. Not necessarily will you be penalized by the college, but if you do it a lot, they take action. But usually if it's a 0 on an exam, that usually means that you failed the class. All right? I don't expect that to be a problem. And then that's the drop day. If you just need to drop, I don't expect you to have to, but if you have other circumstances, then that's the drop day. All right, we good to go on that? Syllabus is online. You can take a look at it. There's an addendum there that talks about disabilities. I'll work with you in whatever way I can, or whatever way you need me to. Disabilities, emergencies, grievances, all that jazz. That's on the addendum. My office hours are here. If I'm not in class, I'm generally available, but these blue sections are my actual office hours. But all these white sections, I'm usually around. If you need to see me, just come on in. Feel free to drop in, or if you don't want to drop in, you can make an appointment. Either way. This is the textbook. You can buy it in the bookstore or online. It says $43 here, but down in the used section, there's some that are a lot cheaper. And I will place screencasts of our lectures from the class every time we meet. I'll place those on YouTube. I use a little desktop microphone, so the sound sometimes isn't that great. But if you just miss something, or even if you miss like a whole day and you just want to catch up and see what material we covered, you can go to the screencast link and you'll find just the audio and whatever's shown on the screen here. I'll write on the screen a lot, so it's sometimes useful for students, especially if you missed class or you missed part of class, or there was just something that you just missed in the class. You were there, but you just didn't get it. So you can use that as a resource, but it's not meant to be a substitute for class unless, like I said, you miss because you had to. Because remember, if you don't come to class, you don't get the class participation credit. And let's see, here's some old quizzes and exams from previous classes. I've only taught this class twice, so this is the spring 2013 and spring 2014. You can use that for what it's worth. And then some of the questions that I ask in class, I'll post here after the class, the concept test. I'll show you what that means later. All right, these will be the multiple choice clicker questions. Those will be useful for studying for the exam. Any questions, John? No? All right. I want to take your pictures. So what we're going to do now is a couple of things. I have up here some slides that have your names on them. So in just a minute, Corey, Taylor, and Jason will come up. I just want you to stand under your name. I'm going to take a picture of you. This picture is not going to go online in any way. I print it out and I put it in a folder. I have like my own little Facebook. It's like a real Facebook. And like I said, and so it just allows me to learn your names. It's important to me that I learn your names. So please help me with that. In the meantime, while the students are coming up, I want you to take out a sheet of paper. This isn't a graded assignment, but please just take out a sheet of paper and write your name on it. And then I want you to write a couple of sentences about why you value higher education, or what you're doing there, right? So right now, all of you are engaged in some sort of four-year program, or maybe even preparation for some professional school. And I want to know what values cause you to do that. So these can be different, right? There is no wrong answer. So for example, like when I was in college, I was probably overly idealistic and it was just like, well, I want to learn new things, right? And well, that's really great. Like I love people like that. That's not very realistic because really, when you're in higher ed, you also like you're trying to do something practical, something useful. And I'm sort of in that place now, like in seminary, trying to do something useful. This is very useful too. But like I'm going to school towards an end. So anyway, just what are your values? You know, maybe it's just you want to do something that your parents never did, which is also me, because my parents never went to college or never finished high school. Or maybe you want to, I don't know, maybe you have children and you want to provide a better life for them. There can be all sorts of answers to this. What are your values that motivate you to come here? Right? And if you would, right now, these four folks come up. Corey, Tate, Taylor, and Jason. One, two, three. Very good. All right, Janelle, Andrew, Brianna, or Brianna? Brianna, and Emily. Emily, Andrew, and Brianna. One, two, three. Very good, thank you. All right, Kristen, Michael, Caitlin, and Brett. Kate. Brett. Michael, Kristen. All right. Now 1, 2, 3. You. And Kylie, Alicio, Patrick, and Chen. Patrick? Phase 1, 2. Excellent. And Noelle, Olivia, and Alyssa. Olivia and Noelle. 1, 2. Kaylin, Duana, and Joshua. How do you say your name? Duana, is that right? And Kaylin? All right, 1, 2, 3. For Josh or Joshua? Josh. Almost, oh, we are done. Anybody I didn't get? Or anybody want to do a retake, like another picture? Okay, I got everybody then? Okay. If I took your picture, that means you were on my roll, so, at some point. I'm still working on your paragraph? So I'm going to give you a minute. So more. I'll run out and grab a drink of water. I'll be right back. Anybody on that yet? Brett, is that right? All right. Okay. Anybody else I didn't get? No. All right, I won't show these to anybody else. They're just for me. Okay. Okay, so when you think of physics, what do you think of? What is it that the study of physics is? Lots of formulae, yeah. There are formulas. We like to think of them not as formulae, but as relationships. Yes. So, like the relationships between different variables. Like when you're in a math class, right, you use formulae. But when you're in physics, you use what? Relationships. Yes. So, how does one variable change when you change another variable? And so we'll look at that quite a bit, actually. Not a whole lot of formulas in this class, and actually, I'll probably give you the ones that you need. But most of them are pretty simple. Right? What else do you think of study physics? Yeah, lots of physics in the muscles, right? And we'll talk about that, the different types of muscles and what they do, and how they make our bodies move, and how we can use our muscles to move other things, levers and stuff like that. That'll be in chapter 1. What else about the human body is related to physics? Lots of pressure. We have a whole chapter just on pressure, right? Not just in the human body, but then also how we administer things like drugs and what have you through the use of pressure. Some other things as well, like the iron lung. We'll see how that works with them. We don't use those anymore, I suppose. But what else? So we have some big topics here. We have like kinematics, that's the study of motion and forces. That'll be chapter 1. Pressure and fluids is another chapter. I forget which one it is. What else we say? We said muscle, but that's like with forces. What else? Physics in the body. We have a whole chapter on thermal physics, right? Which is the study of how heat energy flows from one object to another, and temperature is a measure of that heat energy. So yes, we'll deal with that. We'll do calorimetry, which some of you may have done before. We use calorimetry for a number of different purposes, right? To measure the basal metabolic rate of the human body, which I'm sure you all studied that before, correct? BMR. All right. Any other things? A couple big topics that we're missing out related to the human body, physics of the human body. Sound, right? So we have a whole chapter on sound, and we'll look a lot at the ear, which is really an amazing organ. Like it's probably one of my favorites. Just the way it works is quite amazing. And so we'll look at the physics of sound, how we describe sound, frequency, wavelength, all that jazz, which you've probably seen in high school. But also how the ear works to take those sounds and translate them into something that means something to us. One other thing that we'll study this semester. The eye, thank you. Yeah, so we'll study. Did y'all see me get my eyes real big? I was trying to give you a hint. Did it work? Did y'all know you just weren't saying it? Yeah. So we'll look at the eye, which is actually the ear is probably my second most favorite organ. The eye is probably my first favorite because we just don't really have anything like it. Like detectors that we use to detect light, we can make detectors to detect a lot of light, right? Or we can make detectors that detect just a little bit of light. But did you know that the human eye can detect just a couple of photons? Like if you're in a room and there are just a couple of photons in it, your human eye can detect that. And it's very difficult for us to create instruments to do that. And the instruments that we do create to do that, you take them out in the sunlight and they're dead, right? They just can't handle that. So the human eye is quite amazing. And not only is it amazing, but it lasts, 70, 80 years. You have some issues with it, but for the most part, it lasts for your whole life. So we don't really have scientific instruments that do that work in the same way as the eye. And so we'll look at light, geometric optics. The eye uses lenses in order to focus light, and we'll study how that works. So it's really quite amazing. The eye, probably my favorite. What's your favorite human body part? The what? The knee? Really? All right, there. Okay. Any other favorites?
She asked me why.
What did you say?
Because it only goes one way and there's not too much easy to it.
Oh, okay. I'm not sure that's true.
Well, you can you can do a lot to it, but
Okay. Well, physics in general is about answering questions, and often we can start with very simple observations that will go into answering very complicated questions or very profound questions. And this has happened over, over the past centuries since we really started studying science. First, I want to start out. I have a video I want to watch. Let's see. This is a TED Talk. You ever watch the TED Talks on YouTube? They're pretty interesting. And actually, you can download them on your iPod or whatever. You can do the TED Radio Hour. They're pretty interesting. They sort of summarize the TED Talks. let's watch this one. This one is a guy talking about sort of the history of science and how these simple ideas lead to these profound discoveries. And, you know, this may seem a little bit out of reach, but really simple ideas can lead to big discoveries in your field too. Because I guarantee you, if a person has a bum knee, having a solution to that is a big deal for them. That would be a profound discovery for them if you can help somebody come out of an injury or rehabilitate them, whatever. So, but this is talking about just some major ideas that have shifted over the past a couple millennia, I guess. All right, so the first thing I want to talk about are physical measurements. As much of what we do, much of what we observe, we're actually measuring something. We're measuring the length of something, we're measuring the mass of something, we're measuring the brightness or the loudness of something. And so the measurements, how we measure these things are extremely important. We use particular units whenever we're making measurements. We call the units that we use in physics are called SI units. This is short for, it's French, System International. The International System of Units. It's actually like système, I think there's an accent there, international. I don't know how to write it in French though, but I'm just going to write it. International. All right, are the SI system of units? Within the SI system of units, we have several different categories. We have something called the Mks System and the Cgs System. These are sort of subcategories of that SI system of units. In each of them, we have three things. What do you think are the three basic measurements in the MKS and the CGS? Just a hint, the M and the K and the S are abbreviations for the units. But what are the three measurements that we'll want to make? What's some basic fundamental measurements? Okay, volume is actually a combination of other things. So you multiply things together to get volume. So I'm looking for something a little more fundamental than that. The volume, if we start, where do you back up from to get volume? No, not to get volume. Well, the mass is one of them. Mass is one of our three fundamental measurements. What do we need to find the volume of an object? Distance, or length. So we have mass, length, and then there's a third sort of basic SI unit. What is it measuring? Is that what you said? Time, right. So we're looking for measurements of mass, length, and time. So within this System International, we have the units for mass, length, and time. There are actually some other units that we'll get to later in the semester that have to do with electrical charges and light. I'm not going to present those right now. But everything that we need, we can gather from mass, length, and time. So for example, area and volume, we can get from length, right? If we have the dimensions of something, we can find the area or volume. Or if we want to know the weight of something, we can find that from the mass. And then time we can use along with length to express velocity and acceleration and what have you. Now, the system that we use is the MKS system. That is M for meters, K for kilograms, and S for seconds. You'll need to know what are these three. You'll also need to know what are the standards, which I'll go over in just a bit. The CGS system, just as an aside, the CGS system is used by some other scientists, like for example, chemists use the CGS system, and astronomers often use the CGS system. If the MKS is meters, kilograms, and seconds, what do you think CGS stands for? Centimeters, grams, and seconds. It's the same. So the unit for time is the same. So CGS is centimeters, grams, and seconds. The fact is, most of y'all will use what system? Okay, yeah, in the medical field, you often use the CGS system. We also often use the British system, where we use pounds and what have you. So pounds and miles. And anybody know what the unit for mass in the British system is? The system that we use? It's not pounds. That's a measurement of weight, which is different from mass. This is just a quirky little thing. The unit for mass in the British system is the slug. Isn't that cool? Like, it's not really the coolest thing. They pick up a few slugs of sugar at the grocery store. Right. So, anyway, those are our different systems. We need to know what are the different standards. So anytime we're making a measurement, really all we're doing is comparing one known value to an unknown value. So for example, I have this ruler, and if I want to measure something, I just hold the ruler down and I measure the length or whatever that I want to know of the unknown object. And so what I'm doing is I'm comparing this known object, this object that has a known length, to an object that has an unknown length. And by comparing them, then I can say, well, the length of this object is what, right? So I'm comparing a known object to an unknown object. When we talk about standards of measurement, that tells us how well do we know this known object. All right? So for our mass, length, and time, we have standards of physical measurement. And this seems sort of esoteric, but it's actually quite important that we know these very well. You need to know what are the standards for these three: the meter, the kilogram, and the second. All right, so first of all, the meter is the distance that light travels in a particular amount of time. And that time is actually 1 over 3 times 10 to the 8 seconds. You don't need to know the number, but it's the distance that light travels in a particular amount of time. In 1 over 3 times 10 to the 8 seconds, light travels 1 meter. It used to be that the meter was described by a particular bar in France. Why would that be a problem, to have the meter described by an object located at a particular place? France. Maybe. Why is that an issue? If you're describing your meter, you're defining what a meter is by a particular object that's located in a particular place. That's the main reason, right, Caitlin, right? Yeah, the main reason is that not everybody has access to it. So whenever you're talking about standards, there are some things that you want to have. First of all, you want it to be accessible. And if you have a particular bar in France, that's not very accessible. It was a metal bar, not like a bar like where you go to have drinks, but like a metal bar. And they housed it in a special lab, and it was controlled and kept safe and all that business. But it was still a particular object in a particular place, and not everybody had access to it. So if you wanted to measure something, then you'd have to go to France and find this meter, right? Right? Okay. Obviously, we make copies of those, and that's what these rulers are. These are just copies of the standards that are housed somewhere. All right. What's another reason that the meter, this bar, might be a problem? You probably don't know, but the fact is, with this meter, it can change. Like if you change the temperature of this metal bar, it's going to change its length. Right? Or if you, over time, just the metal that it's made out of can lose atoms. And that's been a problem, actually, for another standard that we'll talk about. So you want your standards to be unchanging. So your standards should be accessible. They should be unchanging. All right? And if you have a particular object, particular objects change. But the speed of light, as far as we know, does not change. So that standard is accessible to everyone because everyone has light, and it's also unchanging. Right? So those are a couple of things that you'll need to think about as we're thinking about standards. And for the standard for meter, which is actually a pretty good standard, is good because it's accessible and it's unchanging. The standard for the kilogram is a cylinder It's actually a platinum iridium cylinder in a particular place. Where do you think it is? It's in France. There you go. So it's a cylinder in France. This has a lot of problems. It's not accessible to everyone, and it's actually not unchanging. This cylinder in France was created, I don't know, probably 100 years ago or whatever. And over the years, they made copies of it and sent them all around the world. So that made it accessible to scientists around the world. But they found that the mass of the cylinder was actually changing. That over time, sometimes the cylinders would get more massive, and sometimes the cylinders would get less massive. And so this was a big deal because this second criteria was not being met. That this standard was not unchanging. So now they're trying to create a new standard for the kilogram, and that new standard is the mass of a particular number of silicon atoms. All right, so they say then they create this sphere of silicon. I'm going to show you a video about it in just a second. A sphere of silicon, and you can calculate how many atoms are in that silicon, and they say this is a kilogram. And then your standard becomes, okay, a kilogram is 1 times 10 to the variable, however many atoms this is, a lot of atoms, that many silicon atoms. Right? And then your kilogram isn't being described by an object, it's being described by a physical constant that's unchanging and that's accessible to everyone. And then finally, so the kilogram is something that's in flux right now and changing. The final thing is time, or the second. And the second is based on the frequency of the cesium atom. All right, so some atoms oscillate back and forth at a very regular frequency, and with the cesium atom, that frequency is very well known, and so we've described the second as it's like a billion oscillations of the cesium atom. And we say that 1 second is when that atom is oscillating back and forth a billion times, and then that becomes our standard for the second. Now that might seem kind of mundane to you, but it actually has a lot of applications, especially with mobile communications, because whenever you're communicating through satellites and through in a mobile way, like through these wireless devices, then it's very important that they're timed properly. It's a very great accuracy. And if you don't know the standard for your time, then it's going to be difficult to have that function properly. Right. So those are our 3 units of measurement: the meter, the kilogram, and the second. You need to know what are the standards, the distance that light travels in this amount of time, a cylinder in France, but also know that this is changing right now because this standard is not a very good standard. And then finally, the second is based on the frequency of the cesium atom. Does this meet the 2 criteria that it's accessible and unchanging for the second? Is it accessible to everyone? You don't think so? Everybody can get cesium. And while it might not be that easy to find the frequency of a cesium atom, it's not undoable. So it is accessible, and it's unchanging as far as we know, that the frequency of these atoms don't change. All right? You're probably not going to run out and get a cesium atom and put it on your wristwatch or anything, but it's accessible and it is unchanging. I have a short video. It's about the kilogram and what's happened to it over the ages. It's actually quite interesting. This is from Veritasium. Do you ever listen to Veritasium? It's a YouTube channel. You'll see, we'll show several things in this class over the course of the semester. It's quite interesting. I think it's interesting. And then like when I find that something's interesting, I really expect to see great excitement in the class. I want to see lots of like eyes popping out of your head. And anyway, this might seem a lot like the standards like for the bar with the meter, but it's different. They're not creating a sphere to be the standard. They're creating a sphere that's exactly 1 kilogram, and then they measure the diameter of it, and then they calculate how many atoms are in that sphere. And so it's not the actual sphere that's the standard, it's the number of atoms that's the standard. The number of atoms of silicon, of this 1 kilogram sphere. The number of atoms that make up 1 kilogram. All right. Let's see, we get out here at 10:20, is that right? Yeah. All right, I want to go over one little thing on unit conversions, and then you're going to do a little activity right before we get out. You've probably done unit conversions in high school or even middle school, is that right? Are you converting from one unit of measurement to another? Yeah? Maybe? Maybe not? Okay. We're going to do some unit conversions. Let's say that I have a particular unit. Well, let's say I have, well, let's say 1 kilogram. And let's see, a kilogram, does anybody know what it is in pounds? 2.2. You know what, I always use Google for this. Google is super. I don't know what we did before we had Google. You can say 1 kilogram equals how many pounds? Now look, 2.2. Who said 2.2? Very good. All right, so Google's really nice for conversions, but of course you don't have Google all the time with you. So let's say that I have 1 kilogram, and it's equal to 2.2 pounds. All right, this is my unit conversion factor. And I can use it if I have a measurement in one system and I want to convert it to another system. So let's say, for example, I had 10 kilograms and I wanted to know how many pounds that is. And I don't have Google where I can go and look it up, right? So if I want to do this, I say 10 kilograms and I multiply it by the unit conversion, not fraction, this should be factor, I'm sorry, by the unit conversion factor. And I set it up in such a way that my units cancel out. All right, so notice here that my kilograms divide out. And so I'm left with 10 kilograms is equal to 22 pounds. We're going to do a similar thing where you're going to measure the length of something in some units that you just sort of make up. And then you're going to create a unit conversion factor, and then you're going to measure and then you can calculate then what is your measurement of that in an actual unit. All right, so we're going to break into groups of about 2. There might be one group of 3, 4, 6. Yeah, there'll be one group of 3. So everybody in a group of 2. And what you're going to do is take some object to measure the width of this desk. All right, your pen. So for example, you might say, this is my pen. What's your name? Noel, right? You say, Noel's pen is my standard. This is my standard for length. In all the world, we're going to use Noel's pen as the standard for length. Or at least in your little group of 2. That's going to be your standard. And then you take her pen, and you say, well, this is 1, 2, 3, or however many pens across it is. And you just estimate what is the fractional of the last one. All right, so you'll get some measurement. And then you can come up, get a ruler, and then using centimeters, the centimeters on the ruler, of course, are the short side. Centimeters about the width of your pinky. And then you can measure what is the actual length of Noel's pen, which is your standard. And then you can say, well, Noel's pen is about 16 centimeters long. So 1 pen equals 16 centimeters. And then that'll be your unit conversion factor here. All right? So what I want you to do is I want you to break into groups of 2. Here, Noel, thank you. And you're going to measure the width of your desk, right? And then you're going to come up to me and you're going to report what is your width of your desk, both in your standard, Noel's pen. You also want to know your unit conversion factor, and then what is the length of the desk in centimeters after you convert that. All right? Let's go and do that. We have about 15 minutes. That should be plenty of time to finish that up and show the results. Emily? Is that right? Jason, is that right? Corey. Who's Jason? Where's Jason? Jason? You're Jason. Corey. All right, so as soon as you get your numbers, I'm looking for 3 numbers: the length of your standard, the width of your desk in your standard, and then the length of your desk in centimeters, which you'll measure with your blackboard or anything like that. Once you get those, just bring it up and say, I want to put them on the board. Everybody clear on what I want? What's your value? Thank you, Brianna. Corey, Mark, Mike, and huh? All right, guys, if you're done with your measurements, bring them up to me, please. So on the first exam, I would expect some unit conversions between just going from one unit to the next. I'll give you that factor. You also need to know those standards, what they are for the Mks system. Bring them on up, guys, when you get them, please. What you got, Mike?
14 centimeters, 5 phones, and 60. Kristen. device.
An iPhone. And it was 12.4 centimeters.
Okay.
And then it was 4.5 iPhone. And it was 55 grams.
Olivia?
We had Janelle's phone,
Gosh, you all use phones?
and we had 13 centimeters and 4 iPhones, and it was 57.
Okay.
We used
Caitlin?
yes.
Yeah.
We used an iClicker. It was 14.7 centimeters. So we used 3.5 iClickers, and it was. Do you want the actual centimeters?
No, how you converted it?
The 51.4 buckets.
Okay, very good. Okay. 14.5?
14.5.
3.5.
Standard. With and then 53.
Okay, very good. Yeah, Taylor.
We used a pencil.
All right.
And it was 14.5 centimeters.
All right.
And then 3.5. And
Okay. Me, Tate, and
No, what's your name?
Caleb.
Caleb.
Yeah. We did cell phone. The desk was 4.5 phones. One phone was 12 centimeters. So 4.5 times 12 centimeters, 54 centimeters for the desk.
Okay. Kylie? Is that everybody up? All right. Let's see, I haven't measured this yet. I'm going to measure it. And you know your measurement? Yeah, right. I think your measurements can vary, right? If you go over here, whatever. I'm just going to sort of go right here. So 0. Like 55.2. Who's the closest? Who is that? The third one now. 4.4, 4.5. That was y'all? Alright, but all these are really close, as you can see. But obviously we have certain errors that are introduced because, you know, an iPhone isn't the best thing to measure the length of the desk with. In fact, a ruler isn't really the best thing either. It's a little small. But unit conversions, y'all clear on that? How to convert between one unit to another? You can probably see one question like that on the test. Also, 1 or 2 questions about unit conversions, or not unit conversions, about the systems of measurement that we use in the SI system. All right, I want to do a little dimensional analysis. I have about 5 minutes left. I don't typically let my classes out early, so we're just sort of not even 5 minutes early. Okay? All right, so let's look at dimensional analysis. You'll have some questions on the exam that are just straight up dimensional analysis questions, but more so it's a nice tool as you look at relationships, right, which is the code word that we use for what? Formulas, right, for relationships, to help us to understand how one variable relates to another. Did I tell you I'm taking a relationships class this semester? You don't know that. It's not very exciting. I'm taking it online though, so I don't actually have to talk to anybody in the course of the class. All right, so dimensional analysis. I think I'll just show you an example first. I think that's probably the best way to show you what I mean by dimensional analysis. But in short, we analyze the dimensions of a relationship or an equation, and it'll tell us whether or not that equation is right. So let me just do one that's not an equation, but it's an expression. That means it's not equal to something. It's just like a mathematical expression. So let's say that I have a length over time. I'm going to use x for my length. Actually, I'll use d for my length and t for my time. So I have d over t. And I just want to know what are the units of that. What are the units of that in the Mks system? Well, length is measured in what? meters, time is in seconds. So what are the units? M and S. In what way are they? M times S, M square root S, M over S, right. So the units of this are M over S. So we just analyze the dimensions. And whenever we do dimensional analysis, it can be useful because it can tell us if some relationship that we're looking at, whether or not it's even possibly true. So let's say, for example, I have an equation where I'm saying that D is length. What was our T is time. And remember, length is in mass. Time is seconds. And then M is our mass. And this is in kilograms. And then also I can have other variables like A for area. Or excuse me, not lower a lowercase capital A. I can have velocity or speed, which has units of meters per second, as we just said. And by the way, area has units of meters squared. So given those variables, let's say that I have an equation that looks like this. Let's say that I say V equals D divided by T. And I want to know, is that equation dimensionally correct or not? Now this was pretty simple, right? Is this equation dimensionally correct? I want to know, are the units on the left-hand side equal to the units on the right-hand side? Well, the units on the left-hand side are meters per second, and the units on the right-hand side are meters for D and seconds for time. And so I would say, yes, that equation is dimensionally correct, because the units, as I've analyzed them, the dimensions are consistent. So I could have another equation. Let's say I have one like this. I have D equals V times T. Is that one dimensionally correct? So you want to write out the units for each. I have D is in meters, V is in meters per second, and T is in seconds. And then I can cancel out one of my seconds here, and I'm left with meters on this side and meters on that side. So is that relationship, is it dimensionally correct? We're not saying that the equation is correct, but at least the dimensions are appropriate. And physicists often don't really think about equations, they just think about relationships. And looking at them in this way can be very useful. So often you can come into a physical situation and you can determine if it's even plausible by seeing if the units match up. We'll do one more and then we'll finish up. I'm going to add another variable over here, which is going to be A for acceleration. We'll talk about these next time, what they mean. But acceleration is measured in units of meters per second squared. Okay. So let's say that I have D equals V times T plus 1/2 A times T. And I want to know, is that equation dimensionally correct? What I want to do is I want to say the units here have to be the same as the units here, have to be the same as the units here. Now we already know that these two are the same, right? These are both in meters. So really the question we're asking is, does this part of the relationship, does it have the same units of meters? Does it? What do y'all think? Yes or no? Can you shake your head yes or no? Okay. What do you do with the half? That has no units at all, so we just leave off the half. A is meters per second squared, and T is seconds. So I have meters per second squared, and T is seconds. And then I can cancel out one of these seconds, and I'm left with meters per second. So is that equation dimensionally correct? It's not dimensionally correct, because I have meters equals to meters plus meters per second. And that just doesn't make any sense. So I would say that relationship obviously can't be true just because the units don't match up. So often physicists and scientists, when they come into a situation, they'll just look at the units and how do they respond to one another. I know it's time to go. So y'all have a good day, okay? Next time, try to have those clickers. We're definitely going to do some clicker questions next time, okay?